In this chapter, we will be looking into gases, liquids, and solids, their behavior and properties, and how we can predict these and use them to our convenience. Now, before we start with that, I wanted to go over some of the key points of Chapter 6, since we're not going to be looking over the whole chapter. Chapter 6 deals mostly with energy. We define energy as the ability or capacity to do work. There are many different types of energy. We have thermal, we have nuclear, we have electromagnetic, but we want to focus on these two mostly, potential energy and kinetic energy. Potential energy is the energy associated with your position and with your composition, and kinetic energy is associated with motion. Now, there is a law that governs all forms of energy, and that is known as the law of conservation of energy, which states that energy in a system cannot be created, nor can it be destroyed. It can only shape form. So I can take kinetic energy, change it to thermal, or even potential energy, and change it to other forms, but I cannot destroy it, nor can I create energy. Now, this is very important, especially when we're considering chemical reactions. If you look at bonds, when we have these electrons as sources of potential energy, then we can better describe and predict these chemical reactions. For instance, one of the biggest principles in chemistry is that molecules are kind of lazy. They really are like us. They want to be relaxed. They want to be in the lowest possible energy state. So if by undergoing a chemical reaction, molecules all go from a higher potential energy to a lower potential energy, then that reaction is likely to happen. And that's something that we can take advantage of whenever we are predicting chemical reactions. Now, energy can be measured, and there are several units that we can use for measuring energy. The most common ones are the calorie and the joule. The calorie is defined as the amount of energy that we need to increase the temperature of 1 gram of water by 1 degree Celsius. Water, the reason why we choose water is because this was done in the 1800s, and water was very common, and it was used as the standard for many different properties, including the temperature scale. So the calorie is, or energy, is no exception. The joule became a little bit, let's say, more commonly used. So the relationship between calorie and joule became widely known and defined as 1 calorie equals 4.184 joules. Now, I want to make this clarification, and that is that this calorie is not the same as the calorie that we see in our nutrition charts. That calorie has a capital C, and it equals 1,000 of these small calories, small c calories. We also call it the kilocalorie, the nutritional calorie, that is. So that means that whenever we're, let's say, ingesting 1 calorie, we're ingesting enough energy to raise the temperature of 1 kilogram of water by 1 degree. That's something to keep in mind. That's why we added the K right here in kilojoules, kilocalories, and so on. Now, going back to our chapter 7, the states of matter. Just as a quick review, we have solids, liquids, and gases. Solids are very rigid. They maintain their shape and their volume, and they're fixed in position by chemical bonds, by these very, very strong interactions. They have high density. The molecules barely move, if anything at all, other than vibrations. And that's mostly because they have very strong interactions with one another. If we look at liquids, liquids have a fixed volume, but they're free to move about, so long as the molecules keep close to each other. Gases, on the other hand, they have no such restriction. They can move however they want. Usually, they keep far some molecules from others, which means that they have random movement, and there's barely any interaction with them, if anything at all. So we say that there's no interaction between particles, making them very low density fluids. Here we have a few examples of solid, liquids, and gases. This is silicon oxide, which is what we have in sand, but also the form of glass is made of silicon oxide. As you can see, there's a pattern there, kind of looks like a 6-tipped star, I guess, with these triangles. And that's normal of solids. They tend to have continuous arrangements, predictable patterns. With liquids, we have no such pattern. They move random, they're just there, moving around. And with gases, they're very far apart from each other. And now, how can we tell if we have a solid, a liquid, or a gas? Well, it'll depend on the kinetic energy, how they are moving, and how they're interacting with one another. Gas molecules have very high kinetic energy. They barely interact with each other. Liquids are somewhere in between. They have some kinetic energy and they have some strength of interaction. Solids lie on the other end of that spectrum. They have very low kinetic energy. They have really huge strength of interaction between these particles, or very strong intermolecular forces. Now, for us to even begin discussing gases, we need to make some assumptions. Gases are very, very difficult to predict. So this set of assumptions, actually, they work really well with experimental data, and they allow us to make some predictions fairly accurately. We call this set of predictions the kinetic molecular theory of gases. Basically, the theory of how gases move at the molecular level. So the first one is that gas particles move very fast and they move in random directions. We can't really tell where one particle precisely is moving. The second assumption that we make is that the size of these gas particles is very small compared to the distance or the space in between particles. Think of, let's say, if I were a gas particle, a person, right? Then the next person or the next gas particle would be so far away that I would not be able to see that person. That's how much of a space there is in between two gas particles, which leads to the next assumption, which is that gas particles exert no forces on each other, no attractive nor repulsive forces. They don't interact, they barely know that the other one exists. The next one is that the kinetic energy, that is the energy of movement of gas particles, increases as we increase the temperature. So if we raise the temperature, the gas particles move faster. And the last one is that if gas particles collide with one another, there is no transfer of energy, no crash, no anything. They just rebound, change their course, and keep along, each one in their own direction. Now, one thing that we can do, we can measure the pressure exerted by a gas, which is nothing more than the average rate of collisions between gas particles and the wall of your container, whatever that container may be. Pressure, we define it as that force divided by the area occupied. And we have several units used for measuring pressure. Which unit are we going to use? Well, it really depends on context. In some cases, the atmosphere will be a little bit better, or the millimeter of mercury, these two right here, mmHg, that's millimeters of mercury, or ATMs, or atmospheres. We can also use torr, pounds per square inch, or psi, or we can use the Pascal. And we have the relationship between them, or among them, right here. Now, there is some behavior that we can predict. We know this as the gas laws, and we can tell by looking at what we call the thermodynamic variables. These are 4 things that we can change and see how the others change accordingly. So there are 4 variables. The first one is pressure. The second one is the volume. The third one, is the temperature. And lastly, the number of moles, or the amount of gas. So all of these gas laws are based on keeping 2 of these 4 properties fixed and then changing the third one and see how the fourth one behaves. So in this case, Boyle actually kept the temperature and the amount of gas fixed. So we're not looking at these 2 at this point. And we see how pressure changes when we change the volume. So it turns out that volume and pressure are inversely related. What that means is that if I increase one, the other one decreases. So if I reduce the volume in a gas by, let's say, half, then the pressure gets doubled. And that's a very important relationship. We take this fish-looking symbol right here. This is the Greek letter alpha. It means proportional to. We can take that away and turn this into a mathematical expression, and we can say that the volume equals a proportionality constant over my pressure. If I move my pressure to the left side, I can say that pressure times volume equals a constant. And this is important because a constant will not change. That's why it's called a constant, right? So if I have an initial set of conditions, let's say pressure 1, volume 1 equals a constant, well, guess what? I can have the same thing under a second set of conditions. If I change one, the other will change accordingly, and this is what we call Boyle's law. Pressure 1, volume 1 equals pressure 2, volume 2. And that's what we have right here. Experimentally, it works really well, and it allows us, under normal conditions, to predict how pressure and volume relate to one another. This is the type of problem that we get to see when we're looking at Boyle's law. We need to look at our variables. Let's say we have volume here, we have pressure, and we have volume again. There's going to be several gas laws that we're going to be looking over. It's very important that we identify our variables so that we can identify which equation we're using. There's only one equation that gives us volume, pressure, and then another volume. That's going to be Boyle's law. If we have these three, we need to find a fourth variable. So what pressure does the gas exert? So we're looking at a different type of pressure right here. If the volume is increased to 6 liters, so we're looking for that P2. So it's just a matter of doing a little bit of algebra. We rearrange our equation, just like the one that we have right here. P2 equals pressure 1, volume 1 over volume 2. And now, this is very important. The units that we use for either pressure or volume, they're irrelevant. It really doesn't matter. But they have to be exactly the same. So volume 1 and volume 2, they can be liters, they can be milliliters, they can be cc's, it doesn't matter, so long as they're both the same, so that they cancel each other. As you can see here, liters cancel with liters, and that's why it's important that they're both the same. And then we're left with atmosphere, which is a unit of pressure. Now, why is this important? Well, one very important application for Boyle's law is when we're breathing. When we inhale, what we're doing is that we're expanding our lungs. When the volume of the lung increases, the pressure inside of the lung decreases, it goes down. Because the pressure inside of the lungs is lower than the pressure outside, or the atmospheric pressure, then air rushes in to equalize that pressure. We get air in. When we're breathing out, the lungs are actually compressing. They're pushing in, the volume is getting smaller, so the pressure increases, the air rushes out, so that the pressure lowers back to normal once again. That's how breathing works. It follows Boyle's law. Now, the second of these gas laws is what we call Charles' law. Now, looking again at those thermodynamic variables, again, pressure, volume, temperature, and amount, well, Charles decided to fix the pressure and the amount of gas. So we're not looking at these two, we're looking at how volume and temperature behave. Well, turns out that they're directly proportional. So if I increase the temperature, or the pressure increases in order to maintain a constant pressure. So that means that volume and temperature are directly proportional, and we end up with this relationship right here. Volume over temperature equals a constant, which means that under different conditions, if I change one, the other one changes accordingly, in order to keep that constant, to have the same number as a result. One example of this, we have here like an island or something along those lines. When cold air moves in, the warm air actually rises, so that on top of or very high above, we have very warm air, and then the cold air just stays below. And that is mostly because warm air occupies a bigger volume, so it has to expand, it has to rise in order to occupy that volume. You can see that in your own houses during the winter time, the warm air of our heaters, it actually goes up. So if you touch the ceiling, is much warmer than if you touch the floor. The floor is mostly cold most of the time. That is because of Charles' law. The third law is called Gay-Lussac's law. It's also known as Graham's law. A lot of people actually arrive at this conclusion at the same time. And in this case, they fixed the volume and the amount of gas, and they worked with pressure and temperature and see how they changed. Well, turns out that if you increase the pressure, the temperature increases as well. But, and this is a very important, let's say, clarification, the temperature has to be in Kelvin. It cannot be Celsius, it cannot be Fahrenheit, it must be Kelvin. So, as a quick review, we changed from Celsius to Kelvin by grabbing our temperature in Celsius and adding 273 to it. So just something to keep in mind. This temperature has to be in Kelvin. And once we do that, we end up with the relationship that we have right here, Gay-Lussac's law. As you can see, this is what we have as Gay-Lussac's law. Pressure 1 over temperature 1 equals pressure 2 over temperature 2. When we combine all of these three, we have what we call the combined gas law. So if, for instance, let's say that we're working with pressure and volume, that's Boyle's law, well, temperature is fixed. That means that T2 and T1 are the same, so we can just get rid of these. Now, that top part looks a little bit familiar. That's because that is Boyle's law. And you can do the same thing for either fixing the volume or freezing the pressure, and you end up with the other two laws. That's why this one is called the ideal or the combined gas law. If you were to memorize one equation, so long as you're able to properly analyze your problem, just by knowing this one, you should be able to do it right, instead of having to memorize 4 equations instead. So, as a quick summary, we have Boyle's law. It relates pressure and volume. Right, we have it right here. We have Charles' law. It relates volume and temperature. Gay-Lussac's law, pressure and temperature, and then the combined gas law.